Hello, everyone. This is James Lee, and this is the Golf Ball Dimple Project. So, a little bit about me. I love golf and I love math, and I wanted to combine these two things to figure out what the optimal dimple pattern on a golf ball is. And I started like researching this and looking stuff up and trying to solve this problem, and it kind of felt impractical with the flight time and the air resistance and the spin rate and the wind, things like that. So I decided to just find nice arrangements of points around different dimensional spheres. So before I start, I wanted to say thanks to Mackie. He's my outside of school advisor for helping with this presentation. So the PGA, the inspiration for this project was obviously from the actual golf ball. So I wanted to take some of those rules and implement it in my new question. So the PGA requires some sort of symmetry, but I wanted to stretch that further, one step further, to perfect symmetry. So my question to answer is, what are some perfectly symmetrical patterns around different dimensional spheres? So each point represents the center of a dimple, and we care about the center of the dimples because it can find the angle between them, and that has to do with how much space the dimples cover, which just relates back to the original question, the inspiration. So part one, there are two parts. Part one is regular patterns. Part two will be irregular patterns. This is a chart of some of the five regular polyhedra in dimension 3, their names and the number of points or vertices, however you want to call it. And at the top, you'll see this notation 2, n, 360 over n. And that just means dimension 2, n amount of points, and 360 divided by n is the angle in between each point. And that always exists because in dimension 2, you can put as many points as you want around a circle, so long as they're equally spaced. The angle will always be the same if they are equally spaced. So before I go into further proofs, I wanted to get this out of the way. It's the dot product. If the vector v has coordinates v1, v2, v3, and w has coordinates w1, w2, and w3, v dot w will be v1 times w1 plus v2 times w2 plus v3 times w3. And in general, v dot w equals the length of v times the length of w times cosine theta, where theta is the angle in between the two vectors. So an example is 2, 3, 120. Angle is 120 because there's 3 points around a circle. I think everyone knows that it's a 120-degree angle. And then if we take any 2 points, let's say we take the point on the bottom left and the right, and we use the formula. So the dot product of the two will be 1 times negative a half, which is negative a half, and negative root 3 over 2 times 0, which is 0. And by the way, the way I got all these points is this is just a regular unit circle, and then the 2 points on the left are from, or all the points actually, are just from basic trigonometric functions. So the length of the vectors is 1, right, because it's a unit circle, which means that the v and the length of the v and the length of w actually cancel out in this case. They just kind of go away because they're 1, right? So we get negative a half equals cosine theta, and arc cosine of negative a half equals theta, and arc cosine of negative a half is 120. So that proves this true. And that's just an example, actually. So for every dimension d, 2d, 90 will exist. And this is true because in a 2D plane, you have a 90-degree angle with 4 points, right? Like this diagram shows. And if you want to have another 90-degree angle in 3D with 6 points, which is 3 times 2, you're adding one more axis compared to 2D, right? And when you add that axis, you're going to have 2 poles on the axis, right? One at the highest point and one at the lowest point. And in the middle will be where this 2D plane intersects that. So that means to add 2 points, you're going to add one at the top of that new axis and one at the bottom, right? So, and then when you do that in 4D, it's the same principle, even though it's a little harder to visualize, and then same in 5D. And you can just generalize it to whenever you add a new axis, you add 2 points with the axis at each pole, and that just proves this true. So here's the triangle case. This is just a unit circle. I showed this a couple slides ago. And what are some other nice polyhedra? So to get from a triangle to a tetrahedron, you can use the dot product formula and the distance formula to actually get there. So if you label all the points here, 1, 0, negative a, if you basically just put negative a as the z coordinate for the previous 3 points and add a new point, 0, 0, b, you get coordinates like so. And because by the distance formula, it's true on this and on the one before, the distance between any of the points is 3. So, or root 3, my bad. And by the distance formula, a plus b is root 2, because if we take these 2 points labeled on the bottom left, what we get in the distance formula, which has to equal root 3, because the distance between any 2 points is root 3, is the square root of 1 plus 0 plus a plus b squared, which means that a plus b squared has to equal 2, so a plus b is root 2. And then when you average the points together, all of them, you should get 0, 0, 0, right, which is the center of that sphere. So by averaging out the z coordinates, you get b equals 3a, because there are 3 a's and 1 b. And then that means that a equals root 2 over 4. And then by plugging in a and b and the coordinates of these vectors into that dot product formula, you get this fourth to last line, which is negative a b times or equals b times the square root of 1 plus a squared times cosine theta. And then if you simplify that a little, divide through by b, and then divide through by square root of 1 plus a squared, move the cosine over, you get the second last line. And then by plugging in for a, you get arc cosine of negative 1/3 equals theta. And then from tetrahedron to four cell, which is like the fourth dimension kind of variant of triangle and tetrahedron, we can kind of do the same thing. And you may have noticed a pattern already. If you didn't, I'm going to tell you. For the triangle, the distance or the angle between all the points is arc cosine of negative 1 over 2, and 2 is the dimension. And then for the tetrahedron in dimension 3, the angle between them was arc cosine of negative 1 over 3, which is also the dimension. And then this is also true in the fourth dimension with the 4 cell. You take these coordinates on the left, I just added a new variable, and then the distance between all the points is still root 3. And then by the distance formula, you get this, 9 over 8 plus e plus f squared equals 3, and that simplifies to e plus f equals root 15 over 8. And then all the points still average out to 0, 0, 0, so 4e equals f, and e equals the square root of 15 divided by 8 divided by 5. And then by the formula, the dot product or the angle formula, negative e times f equals f, times the square root of 9/8 plus 15 over 8 over 25 times cosine theta. So that means that negative e equals square root of 9/8 plus 3 divided by 40 times cosine theta, blah, blah, blah. And then a little bit of simplification there. So negative e equals the square root of 6 over 5 times cosine theta. And if we divide by, or plug in for e first, doesn't really matter the order, and then divide through by root 6 over 5, and then move the cosine over, we get this third to last line, which is a little bit complicated, but by just simplifying that a little, it's a little bit difficult to simplify, but it's not too bad. You just get that all equals negative 1/4. So arc cosine of negative 1/4 equals theta. And then those three examples all fall into this conjecture that in every dimension, d comma d plus 1 comma arc cosine of negative 1 over d will exist. And then three examples support that, so you can make a really good educated guess. All right, and then part 2 is the irregular patterns. So this is from the golf ball patent, and as you can tell, it's not perfectly symmetric about every possible axis, right? Because there are like 4 chunks, kind of like quadrants, I guess, on the top, then 2 like rings or bands in the middle, and then 4 more quadrants or chunks on the bottom. Kind of harder to see in these diagrams, but they're there. And then these are some graphs of the first 130 arrangements of points in these 3 dimensions. And we know that most of these are irregular because, for example, in dimension 3, there are only 5 regular patterns, which leaves 125 of them to be irregular, and then the rest that are added to it are also going to be irregular. And then some nice arrangements of points are here. You can see all of them have a nice angle except for 2 of them. And those 2 are special because if you take 3, 6 and you add a point in the middle of each face on that arrangement of points, you will get 3, 14. And that's going to be a nice arrangement. So point, And then if you add a point in between every side length or side, like the line in between 2 points of 3, 6, you get 3, 18. So those are going to also be 2 nice arrangements. Right, and then next steps for this project. I really enjoyed doing this project. And in 8th grade, we do a year-long recital project. And I hope I can extend this project to then. And I think that would be really interesting, and maybe study more of it, like do more irregular patterns, because I felt like I focused more on the regular patterns. Maybe do some of the physics, the air resistance, spin, the size of the dimples, things like that. And then more about the number and the size of the dimples, right? Because there has to be a limit on how many and how big they are, the dimples, that is. And I'd like to figure that out. And that's going to do it for now. I hope everybody enjoyed, and that's it. Bye-bye.